Okay, so I am going to be going through my solutions for this. Like we'll open up ChatGPT's version as well, so so I can check all my answers and check its answers, make sure it's correct. But I'm going to be going through this in real time. I guess I'm going to have to open that separately. Canvas has been doing this lately. Okay, so here's its answers. I'm guessing this is going to take me an hour to get through all this. We'll see. But all these conceptual questions, you can just check here for what the answer is. I'm not going to write all these down. I'm just going to talk through them. Can an object moving at constant speed have a non-zero acceleration? Yes. If you're moving around a circle with constant speed, you still have an acceleration toward the center, centripetal acceleration. When you throw a ball straight up, at the top, velocity is zero, acceleration is toward the Earth. Not necessarily negative. If you called down the positive direction, acceleration would be positive. But no matter what, acceleration points down during the entire trip, and up at the top, velocity is zero. If a car is going around a curve at constant speed, then the direction of the net force points toward the center of the circle, centripetal acceleration. A lot of these are about centripetal acceleration. These are the exact same question. Yes, it's accelerating toward the center of the circle, the Earth. Momentum is always conserved in any kind of collision. Kinetic energy is only conserved in perfectly elastic collisions. If they stick together, there's got to be some kind of deformation going on. In fact, that would be a perfectly inelastic collision. But so kinetic energy is not conserved, but momentum still would be. Let me make sure I'm recording. Okay. A net force can do zero work on an object if the net force is not pointing in the direction of motion. Again, an object going around the Earth at constant speed in orbit. The net force is toward the center of the Earth, but we're not increasing the speed. The work energy theorem says that the total work done by all forces combined must equal the change in kinetic energy over some time interval. If we're going at constant speed, there's no change in kinetic energy. Not all forces do work. If your force is perpendicular to your direction of motion, you're not doing work. The area under a force versus position graph is work. Okay, if angular velocity doubles, what happens to rotational kinetic energy? Well, rotational kinetic energy is I omega squared. So if omega doubles, you would get 4 times the kinetic energy. So we got an object submerged in water. The only thing that determines the buoyant force is the volume of that object. In simple harmonic motion, remember F equals negative kx. So the force is greatest at the outsides, at A and negative A. That's also where the acceleration is the greatest because F equals ma. Velocity is the biggest in the middle at x equals 0. Force and acceleration are greatest on the ends. Potential energy is greatest on the ends. Kinetic energy is greatest in the middle. Okay, now some problems, and I will work through all these. All right, so let's draw a picture. Like I'm going to write up complete solutions here. Here's x equals 0 at 0 and t0 equals 0. Here's x1. We don't know that. Here's t1. We do know that. That's 6 seconds. Okay, we know our formulas, x equals x naught plus v naught t plus 1/2 at squared. V equals v naught plus at, and v squared equals v naught squared plus 2a delta x. Okay, so if we have our knowns and our unknowns, maybe we should be very complete here. Known. So we know x0 equals 0. We do not know x1. Oops. We know t0 equals 0. I'm telling you, if you go through all of this on all of these problems from rest, so v is equal 0. If you go through all this on all these problems, you're going to get a lot more right. We don't know x1. And we don't know v1. Okay, I think we can immediately solve for v1 because we know a. A was 4 meters per second squared. Okay, so we can immediately find v1. And I think if we just plug in here, we could also immediately find x1. So v1 will be v0 plus at1. Remember, these two have to go together. So that's v1 equals 0 plus 4 times 6. That's 24 meters per second. X1 will be x naught. That was 0. V naught was also 0 times t1. So times 6 plus 1/2 times 4 times 6 squared. So that's 36 times 2, I think 72 meters. And let's check just to make sure I didn't goof anywhere. Yep, 24 and 72. Okay, always draw a picture. We got a ball thrown downward. So we're throwing it down here, and I'm graphing t versus y. Okay, let's call this y equals 0 down here. Y1 will be 25 meters. And it looks like we're thrown straight down. So we're not going to have to get x involved here at all. It's kind of a boring problem. And we know v y naught is 3 meters per second. And again, we could do a known and unknown. Like, this is a pretty easy problem. How long does it take to hit the ground? This equation is not going to do us any good. Because I don't know final V. And I don't know time. Two unknowns there. I would have to use this guy. Okay, so y, my final y is 0. Got to be careful here. This is initial. Oh, y is 0. This is y1. Let's be clear there. We're starting up here. Y1. Oh, yep. See, almost goofed there. So this is y0. This is y1. Y1 is 0. Y0 was 25. 3 times t. And then here a is negative 9.8. So minus 4.9 t squared. Then we're going to have to use quadratic formula. I am going to absolutely just look and see what they got here. .97 seconds. But you could do that on your own. Quadratic formula. Kind of a boring problem. I would be prepared, if I were you, to do the kinds of problems where we're throwing this up at an angle and we have to find both x and y components of the initial velocity. And then when we hit the ground over here, if we had x's and y's, finding the final velocity vector, both in x and y. We had a problem like that on test 1. Go back and look at test 1. Make sure you know how to do those problems. Okay, we've got these incline problems. Any of the kind of incline problems, we've had a bunch. This is a 30-degree angle. We've got a 15 kilogram box here, and we're sliding down. I think it's going to be easier, so I don't have to deal with negatives as much if I draw my incline going the other way. So we'll call this 30 degrees, and we're sliding down this way. So that's the direction I'm moving. So what will the forces be on here? What if I can get different colors? Okay, so I'll have weight pushing straight down. I'll have my normal force pointing up perpendicular to the surface, and friction is pointing back this way, and that is kinetic friction because we are sliding. Then, if I rotate my frame of reference so that the normal force points straight up and friction points straight backwards, then my weight vector will point over here. Okay, and if I remember correctly, so look, if this is 30 degrees, then this angle here is 60. That's right in here. Or this is 30. Either way would be fine. I'm going to put the 30 here. That makes this WX and that WY. Okay, so let's break W up into components first. So WX is opposite the 30, so he's going to go with sine 30. So that's mg times a half. Sine 30 is a half. And WY will be magnitude of W cos 30, which of course is root 3 over 2, but we can see from the picture, my y is going to be negative. You got to put in the negative yourself. So negative mg root 3 over 2. Or I could just type those in my calculator. So we'll get those numbers in a minute. Then we know the normal force, sum of the forces in the y direction equals 0. So that implies normal force equals in magnitude wy. So that's going to be, because we're in magnitude, mg root 3 over 2. Frictional force, kinetic frictional force equals mu times n. So that'd be mu mg times root 3 over 2. And that'll be my only force. No, that's not my only force. Sorry. I was like, oh, well, that ain't going to work yet because we've got another force. Some of the forces in the x direction. We've got wx plus, and if we add these as vectors, keeping in mind that one of these is going to be a negative. Okay, so this guy's a positive force. This one's a negative. So what was wx? Mg over 2. And then minus that guy, mu mg times root 3 over 2. And that'll be mass times acceleration. My acceleration is going to be positive. It's going to be here, straight down the hill. This is my x-axis here, right down the hill. And notice here the m's cancel out. It's one of the reasons why I didn't just go ahead and plug in numbers. So my acceleration is going to be a half g over 2 minus root 3 over 2 times g times mu. That was going to be negative. There, needed that mu in there. All right, so again, I don't feel like Getting my calculator out. And that's exactly what we see there. See, there's G times a half. There's mu. That's root 3 over 2. Cosine of 30. 3.20 meters per second squared. And that's down the incline. We absolutely could have just plugged in numbers from way up here. Would have been perfectly fine. Okay. Oh, we got a very similar problem. So I've got a box here, got a rope pulling it up, and this is 25 degrees. Hold by a rope at an angle. Oh, no, no, no. Nope, I lied. We're not going up an incline. Got to make sure I read the problem right. I've got a box. There's just a rope pulling it where this is 25 degrees. And that coefficient of friction is here against the ground. Okay, let's switch back to black now. So my weight will point down, my normal force up, and my frictional force opposes slipping. So we'll point backwards, and we've got some tension force. So let's draw this in a free body diagram. Weight down, friction backwards, normal up, and tension here. And that's 25 degrees. Okay, and we know tension. Now we're going to have to break tension into components. So let's do him separately over here so we don't cloud things up. This would be my Y component. This would be my X component. That's 25 degrees. All right, so Tx will be magnitude of T. He's adjacent to the 25, so cosine 25. Ty, and everybody's positive here. We'll go with sine. All right, so 20 cosine 25. I need to get my calculator out now. Let me clear everything so you're only looking at what I'm looking at. 20 cosine of 25. And let me make sure on the test, make sure you're in degree mode. 1813. And then 20 sine 25. 845. All right, then some of the forces in the y direction will be as vectors, add these as vectors, normal plus weight, keeping in mind one's positive, one's negative, plus ty. And that must be 0. So we can solve for the normal force. Why am I doing this? Because I know the frictional force is some multiple, it's mu times the normal force in magnitude. So I need to find the normal force. So the normal force is going to be when I move both of these to the other side. This guy's going to be negative, he'll be positive. So mg 2.5 times 9.8. See, he's negative here, but on the other side it'll be positive. But this ty will be negative on the other side. Okay, so 2.5 times, times 9.8 minus, you know what you can do is you can do minus second answer to eliminate some of the rounding we had in there. 1605. Okay. Why do we care about that? Because the frictional force in magnitude is mu times the magnitude of the normal force. And what was mu? 0.15. So take that last answer times 0.15, 2.41. Okay, now we can do some of the forces in the x direction. And that's the frictional force plus Tx. That's a K there. And this guy is negative. Like that was just his magnitude there. This guy was positive, so that's going to be 18 minus 2. And I'm going to show you something here. I've got that 2 on my screen here. I want to do 18 minus that answer. Watch this. I'm going to do it backwards. Last answer minus 18. I'm getting the opposite. I'm going to end up with a negative here, but it's the same number. Just a little shortcut you can use to save time. You got to be careful with it. But my answer now is 1559. Type that in your calculator. You'll see 1559. And that's Newton's. I don't even remember what we were asked for. The acceleration. Well, F equals ma. So take that, 59 divided by the mass, 2.5. So again, on my screen is a negative. I'm just going to ignore that negative. Just take that divided by 2.5, 624 meters per second squared. All right, let's see if ChatGPT got it right. They rounded someplace where I didn't. What did I get? 624? And they got 629. So I'm just curious. 18. Yeah, I could probably pull up here where they did their rounding. Oh, it was me right there when I did that minus 18. It was actually 18.13. Yeah. So right there, I did a little bit of rounding. I only typed in an 18 instead of an 18.13. So here, let me pause. I'll clean that up. We're off by 0.13 or something divided by 2.5. All right, let me pause and I'll clean that. Okay. I was trying to show you a little shortcut here. When you've got an answer and you're supposed to subtract that from something. So again, let's say we had the 241 on my screen, 2.40. And my next step is to take 18 minus that. You can just do 18.13 subtracted from this and realize, oh, I'm going to get the opposite of the answer I want. And just ignore the negative. Okay, this is a really boring problem. It does not need a whole page. Work is force times distance times the cosine of the angle between the force and the displacement. Okay, so we got a hiker here climbing up a hill. The whole time, gravity, his weight, is pushing down. His displacement vector is up. So the force will be mg. His displacement is 35. The angle between those is 180 degrees. Gravity is doing negative work here because that's going to be -1. The guy's doing positive work. Gravity is doing negative work on him. So 60 times 35 times -1, 2100 joules. Negative joules. What is the change in his gravitational potential energy? Change in potential energy will be mg change in height. Oh, that's just mg times his displacement. It's exactly the same number, only this one's positive. He has gained energy now. He has gained potential energy. So he did physical exertion and converted that into gravitational potential energy. Let's see how ChatGPT. Yeah, exactly the same. What did we get? Where'd they get that 06 from? Did I? Oh, I goofed. Did I goof? Yeah, I forgot G. I'm sorry about that. mg times 35. Forgot the G. So 60 times 9.8 times 35. 20580 that they rounded off. Joules. Okay. Make sure I'm recording here. All right, this is just conservation of energy. So up here, potential energy is mgh, where this is h. If we call down here, potential energy equals 0, we get to make that choice. So it's just mgh equals 1/2 mv squared. M's cancel out. I would multiply the 2 over and then take the square root. So square root of 2 times 9.8 times 20. And I'm just going to look at this one. Again, didn't really need 19.8. Didn't need a whole page on that. Remember, we had problems on test 2 where we had the roller coaster going up and down. Make sure you look through those. You know, I like those problems. Yeah, I really should have gone through and made some of these half-page problems. This thing could be half the length that it is. All right, power is just work per unit time. We write this, delta W divided by delta T, but work by itself is already a change. I don't like, we write this because in differential form, it's dW dt. And we think of differentials as the limit as delta T goes to 0 of a delta. But we don't have to find two different works. It's just the work. It's better to think of power as work divided by time. So 5.0 or 5.0 times 10 to the fifth divided by 10. I think that's just 5 times 10 to the fourth. Watts. Our units here are watts. And double check their answer. Yep. Okay, impulse is just change in momentum. This is one students always want to mess up because they don't remember what impulse is. So they just make stuff up. It's just change in momentum. It's just a fancy word for change in momentum. All right, so we got to be careful here. Really easy to mess this one up. I've got some initial momentum. I bounce off a wall and I've got some other momentum. Remember, momentum is a vector. So I want P2 minus P1. And I'm going to, this is going to sound weird, but I'm going to call this one the positive direction and that one the negative direction. So I'm calling that way positive. And I'm doing that because I don't want to have to deal with more negatives than I have to. Anytime I got something bouncing, it's easier if you call the final positive so that your leading term here is positive. And these, of course, are vectors. So here I'm going to have a minus and another minus because this guy is already a negative and I'm doing this one minus that one. So it's a positive minus a negative will end up adding those. So this is mass times velocity 2 minus mass times velocity 1, which is a negative. So that'll be 5 times 4 minus negative, or I could write it here if you want, 5 times negative 6. That's 24 plus 30. And that would be, what is that, 54. And mass times velocity, kilograms times meters per second would be my units. Did I read the question wrong? I did. I did. It's 0.5 kilograms. 0.5. So 2.4. So 5.4, is that what the final answer is? Oh my God, I also did 5 times 4 is 24. I'm trying to rush through this because I want to get this done. I'm sorry. 5 times 4 is 24. Okay. 2 plus 3 is 5 kilograms times meters per second. I was thinking here because I was doing 5 times 6 and then I was doing 6 times 4. Okay. I'm not going to do this one. We know we're going to have conservation of momentum, which means MV1 initial. So let's say MVA1 plus MVB1 must equal MVA2 plus MVB2. And then we have conservation of energy. 1/2 MVA1 squared plus 1/2 MVB1 squared equals A2. I want all twos here. I am not going to do this problem because I would not put this on your final. You got to solve that whole system of equations. We know this is a pain. Like if you want to see a complete solution, Chat GPT has just jumped to, it looked up some formula and it found this formula for the final velocities, this set of formulas here. We do not have those on our equation sheet. I'm not going to give you that problem. I'm going to dot, dot, dot that one. Okay, so we got some solid disk. I would give you I here. By the way, I happen to remember this is 1/2 mr squared, but I would give that to you on the test. You do not have to memorize any of the moments of inertia. All right, we want the angular acceleration and the net torque on it. Okay, so it looks like we're gonna have to solve for acceleration first. So our formula's here. Plus omega naught t plus 1/2 alpha t squared. Omega equals omega naught plus alpha t. That's the one we're going to use. And omega squared equals omega naught squared plus 2 alpha delta theta. Okay, we're going to use this one here to solve for alpha, right? Because we've got both omegas. Initial is 0, final is 12, and we've got a time. So 12 equals 0 plus 3 alpha. So alpha is 4 radians per second squared. Okay, we know tau equals I alpha. So that's going to be 1/2 times the mass times the radius squared times alpha that we just found. So that's 1/2 times the mass is 4, radius is 0.25, and we're going to have to square that times another 4. So that's, I think we get a half. I think that comes out to a half. Yeah, torque is 0.5. Let's see, torque here is Newton meters. Is that all they asked for? Yeah, kind of a boring question. Okay. So we got this meter stick. It's supported at the 30 centimeter mark. So my whole thing is 1. This is at 0.3. I've got some kind of support. And then we're going to have to put, obviously, if I put a weight over here, the thing's going to tip. There must be a weight over here somewhere that's going to balance out all the weight over here of the meter stick. All right, let's switch colors again. So we've got some normal force pointing up. We've got this guy here, let's call him F1 pushing down. And then right in the middle at the 0.5 mark, we've got the weight of the meter stick. Okay, so we know some of the forces in the y direction must be 0. So F1 as vectors, F1 plus N plus W must equal 0. So those two are negative, that one's going to be positive. All right. Let us put our axis of rotation. I don't know N, and I don't know F1. Put your axis of rotation at something you don't know. to get rid of it. I'm going to put it here. So this distance here, I'm going to call D. Now I got to be careful here. That's my distance from the pivot. At the end of the day, I want to know this distance here. Maybe we'll call this X from the start of the meter stick. That's what I want. And I could have done that here. I could have just used X, but at the end of the day, I need the distance from my axis of rotation. So I'm going to call this D. Once we find that, we'll subtract it from 0.3 to find this. Okay, so we've got F1 down. And then over here, I know this distance. This is 0.2, where the weight is down. Because from 0.3 to 0.5. Remember, the weight's always at the middle. All right, then torque from F1. This guy's trying to make me rotate like this. So let's call that a positive torque. That'd be D times F1. And then torque from the weight, that's trying to make me rotate around like this. That'll be a negative. And that'll be 0.2 times mg. And those must add up to 0. So D, or F1D, however I want to write it, minus 0.2 mg must be 0. So D will be 0.2 mg divided by F1. All right, so that's 0.2. What was M? 0.25 times 9.8 and 0.5 mass. All right. Yeah, I better type that in because ChatGPT may have done this the other way. Divided by 0.5, could have just done times 2. 0.98. Wait, something's not right there. Did I type 0.2? I either typed something wrong. Let me look through this. I'm going to pause because that answer doesn't make any sense. Oh, it's right here. It's right here. There should be a 9.8. F1 is the force, not just the mass. Those cancel out. So that was the weight of the stick. This is the weight of the box I put on there. The G's are going to cancel out. All right, so that's just 0.2 times 0.25 divided by 0.5. They'd just taken my last answer and divided off in 0.98, 0.2. Okay, but that's not my answer. From here, so I'm 0.2 from here, that's 0.1 from the end. That's at the 10 centimeter mark. And let's see what they did. They got the 20 centimeter mark. I want to make sure I type that. I was expecting The second time I did this calculation, I was expecting to get 0.1. Did you hear the surprise in my voice when I got 0.2? Because I said we could just divide this by 0.98 or 9.8. Yeah, it's right there. Yeah, I keep goofing. I'm supposed to do 0.2 times 0.25 divided by 0.5. This is 0.1. Okay. I knew that answer didn't make sense. This is why you got to think about your answers. Don't just blindly trust your calculator because it's so easy to goof. So this is the 20 centimeter mark. That was meters. Okay. I think we're almost done here. Okay, so like this is literally just plug and chug. F equals capital G, which they did not give us here. I would give you on the test. M1, M2 over R squared. This is 6.11 times 10 to the negative 11th. Something's not right there. I don't have this memorized. I don't expect you to memorize it. 6.674. I think most books just say 6.67 times 10 to the negative 11th. It doesn't matter which order here. I put these masses into the 24th, 6.37 times 10 to the 6th. Here's what matters. R here is the total distance from the center of the Earth, really from their center of masses. But the astronaut's center of mass is just him. We're treating him as a point object. I goofed. Not that one. Second mass, 75. Um, okay. R here is the distance of the astronaut from the center of the Earth. So I have to add this plus this. That's my radius. 6.37 times 10 to the 6th plus 400,000, because I have to be in meters, squared. All right, and I'm not going to bother plugging that in. You're going to get 652 newtons. Okay, this one's kind of tricky. I'm going to have to think through this one. So we've got 60% of the volume submerged. We know the buoyant force. If I draw a free body diagram, the weight and the buoyant force must equal each other because we're floating. We're not moving up or down. So the buoyant force equals the weight. That's mg. But we also know the buoyant force equals the volume or the weight of the displaced water in magnitude here. That weight of displaced water is going to have the same volume as this volume here, because a floating object displaces its own weight. Hold on, I gotta think about this. Yes. A displaced object displaces its or a floating object displaces its own weight. That's literally what this says right here. And the amount it sinks has the same volume. So this weight displaced, that's the weight of some volume of water. The same as this. I'm going to redraw that picture. That volume of water has this weight. Okay, so we know volume. I always have to start with this. Rho equals mass per volume. So volume is going to be mass per rho. If I multiply top and bottom by G, that's weight divided by rho G. Okay, so and when I say weight, I mean the same as this. But the weight displaced will be 8G over rho G. So 8 over rho. 8 over 1,000 cubic meters. Okay, yeah, I think this is going to work. This is a tricky one, like I said. So that's the volume of the shaded region here. Why is that the volume of the shaded region? Because that's the volume of water that would have this amount of weight. Why is it this amount of weight? Because a floating object displaces the same weight in volume of water. Okay, now this volume is 60% of the total volume. 60% is submerged. So this was a volume of water or the volume of the shaded. So the volume total for the object, or we could say it this way, 60% of that volume would be this. So this is for the object. So divide that by 0.60 to get the total volume. So 8 divided by 1,000 divided by 0.60, 0.0133. Okay, I think this is working. Like, wait till we get to the end and I'll look at the final answer. We better end up with a density less than 1,000, but not way less than 1,000 because the thing's still partially submerged. This thing's going to weigh less than water, have a density less than water, but not super less than water, or more of it will be floating. All right, so if that's its volume, his density should be his mass divided by that. What was his mass? 0.8. All right, so 0.8 divided by second answer. Oh yeah, that can't be right. There's no way it's 60. All right, hold on. Let me pause and think about this. Like I said, this is a trick. I think I found the mistake. It's supposed to be 0.8 all the way back here. Because this was my mass here, 0.8. So I bet this is 0.0, 0.0, 0.0. I think we're going to get 600. Let me check this. Point, this is 0.8 here. All right, I think this is gonna work. And I think the answer is 600. So 0.8 divided by 0.00133. Yeah, 600. That was rounded off. So it's 600. Oh, let's see. Kilograms per cubic meter. All right, let's check and see if that's right. And then, yes, it is. Good. I did not know this formula for a floating. And we could probably prove this. That's kind of what we just did here. We kind of proved that the fraction submerged is just a ratio of the densities. So then it's just plug and chug. And like here's it says alternatively, and literally all the stuff I just went through. Wow, that's funny. Like it literally is the same steps I just went through. Okay. Okay. This is going to be easy. We know, let's start with omega. Omega equals square root of K over M. So we're trying to find K. And let's say here implies omega squared times M equals K. Yeah, and then period is 2 pi over omega. So omega is 2 pi over T. So this will imply K equals, we know the mass, and then we're going to have 2 pi over T, all quantity squared. So 0.3, and we're going to have a 2 pi over, what was my period? I don't need the amplitude here until I get to this. 1.2, all quantity squared. So that one's just plug and chug. Yeah, so see, they first found omega, perfectly fine. 8.23 newtons per meter. And then maximum speed, remember V max is A omega. So I guess it would have been useful to find omega. What was A? I'm just going to write everything down here and then write the formula. K over M. So it's just plug and chug. Kind of a boring problem. 262. And that's meters per second. Okay, then the final problem on this one. All right, amplitude, all these are pretty much right in front of us. Amplitude is 0.06 meters. That's the number in front. Wavelength, lambda is 2 pi over K, and period is 2 pi over omega. So 2 pi over the one in front of X. Lambda is a length. It's related to the number in front of length. So 0.5. Period will be 2 pi over the one in front of time. Oh, we got 2 pi's in here. Oh, I got to be careful. They almost tricked me. Distribute that 2 pi. 2 pi's are going to cancel out. Omega is 4 times 2 pi. 2 pi's cancel. Period is 1/4. Lambda equals 2. That's meters per second. But they didn't ask me for period. They asked for frequency. Frequency is 1 over the period. I think we're going to get 4 hertz and 2 meters per second. I'm going to do that kind of quickly. Let me double check my work there. Yeah, lambda is 2 and 4. And then V equals lambda F. So 8 meters per second. Just multiply those together. Direction of propagation. It's moving along the x-axis. That's a weird question. We're propagating along the x-axis, oscillating up and down in the y-axis. Yeah, so technically, that we're oscillating forwards and backwards along the x-axis. You could look at it either way. Okay, questions that were not on here. So other kinds of problems. Somebody throwing something off a cliff. Ooh, and you want to know where it lands, where we're given some angle and some initial speed, like projectile motion problems. Make sure you know how to do all the different kinds of projectile motion problems. Really, if you know how to do this one, you know how to do them all, because that's the hardest one. Well, there's the harder one where they give you 2 different speeds along the way and they don't tell you anything else. Those are like really, really nasty. I wouldn't put that on a test. This is the hardest thing I'd put on a test. Centripetal motion, car around a curve. Problems. Pretty much guaranteed you're going to have one of those on there. Like we did a whole bunch in class. Look at your notes. We had one on, I think it was test 1, where we're either going to find, there are one of 2 things you can find. You can find the minimum coefficient of friction. That's mu sub s, or you can find the maximum speed so that you don't slip. And honestly, I don't. I'm telling you, there's one of these problems on there. I don't remember which one it is, but they're basically the same problem. Oh, let's see. Displacement versus distance. Like conceptual type questions. You know what I'm going to do? I'm going to look at the actual test and see, but I'm not going to show you. Zoom recording. V versus A type questions, like from the very first day of class or maybe the second day of class, where questions are like you're speeding up and moving to the right. Is your acceleration positive or negative? You're moving to the right and slowing down. Is velocity positive? Is acceleration positive? Those kinds of questions. Understanding the direction, the signs of V and A. In this exam we just looked at, there were no sound problems, sounds, and yeah, no sounds. So Doppler, sonic booms, decibel scale. That's how you spell decibel. Decibel scale. Problems like the one we did in class yesterday, where you've got a whole bunch of amps arranged in a circle, adding up decibel kind of problems. All right, pause. I don't want you to see. Calculus problems. So most of what we do, like with projectile motion, we have constant acceleration. What if we don't? How do we get from position, velocity, and acceleration to the other ones? By either taking derivatives or taking antiderivatives. And let's say we did have a rotational motion problem in here, but I'd be prepared to do more rotational motion. Rotational. Like ones where we have constant angular acceleration, where we're using all our rotational kinematic equations. We kind of, like I said, we kind of had one on here. But also like the ones where we have to use torques, like the fireman kind of problem, where, the one from test three, questions like, I'm not saying that exact problem, but questions that are similar to that, or the sphere rolling down a slope, something along those lines could make the cut. Um, yeah, nothing else I can think of right off the top of my head. Let me scan through here again, see if there's anything I want to say. I mean, of course, more conceptual questions. Could definitely ask a lot of conceptual questions about Newton's laws. So definitely questions like this. You're going to have some kind of question where that's along the x-axis with constant acceleration. You might have to find the acceleration, you might be given it, something like that. Definitely some kind of projectile motion problem. Sometimes with these, you can use conservation of energy. If the question just asked, at what speed do you hit the water below? You can just use conservation of energy. You don't have to use kinematics. Yeah, absolutely going to have some kind of inclined plane problem or tension problem like this. Had tension at an angle, but I wouldn't really call it an inclined plane problem. We could easily mix those together. Yes, definitely going to have questions on work and energy. And more conservation of energy. I would be prepared, let me put this on the list, to do an inelastic collision, because the one that was here in this practice test was a perfectly elastic collision. Inelastic collisions are easier. Yeah, that's all pretty simple, pretty boring. My impulse, I'm going to say it again. People always forget about impulse. Yeah, I think we've covered everything. Okay, I think this is a pretty good review. I think that's a good place to stop.